How are you guys doing? Last talk of the day before your Halloween party, but hopefully this will be an interesting one. I'm Andrea. I'm joined on stage by my co-founder, Gabriele, and today we are introducing a new framework for on-chain games. So I'd love to start by perhaps stating the obvious for some of you, which is why even bothering building fully on-chain games and putting the state and the logic on-chain and having to deal with all the intricacy and complexity that comes with it. And the reason is simply to gain properties that we don't have with the traditional gaming infrastructure. Permissionless mods, it's one of these properties, where essentially all of your players and developers can customize any aspect of your game, from the high-level client by introducing plugin or mods, down to the very logic of your game by extending the gameplay with smart contracts. And so essentially is this new paradigm where every game's become a platform by default. And potentially, no matter how small your team is, you can become a content powerhouse. The second one is persistency. There's a big buzz around the autonomous world and how these virtual experiences can last forever because they can be shut down. There's no server that can be censored or shut down. And effectively, what these experiences introduce is a whole new level of significance into games. Games become avenue where players play, but also engage, socialize, conduct global commerce work in a way more pervasive fashion than what is already happening with traditional gaming platform. And the last one is open economies. So the ability to tap into open, global, frictionless payment and microtransaction, especially in our ecosystem, and reuse existing primitives on-chain like DAXs or NFT marketplaces. The problem with these games is that it's extremely difficult to build these experiences. And so we look at the market, and there are frameworks that try to simplify the developer experience. Some of them are really interesting. They're trying to iterate on provable session, where you compute physics off-chain and you prove the integrity of the computation on-chain, or introduce sticking, so loop-driven runtime that are more similar to game engine than event-driven runtimes of blockchain. But the fundamental trade-off that every single one of these frameworks is doing is they're compromising performance to composability. In order to achieve more performance and more TPS, typically you are creating isolation with L3s, or you are introducing different runtimes with shards. And so we're just not comfortable with this trade-off. We ask ourselves, what if there was a framework that has high throughput, that could support us with all the TPS that we needed, with on-demand scaling, so that the moment your game becomes successful, potentially up to millions of players, you don't have to compromise their user experience because there's no gas spike, and you can support this level of demand. And a framework that is customizable with no fragmentation. So you can potentially have those provable game sessions, or even simulate the passage of time with a free transaction scheduler without having to pay a gas fee, but that introduce no fragmentation with isolated upchain or L3s. And so we're incredibly excited to present Bolt, which is a high-performance and composable SVM-based on-chain framework. Bolt is modular. Bolt is modular and is composable. It works with all of the existing infrastructure on Solana. It works with our primitives, on-chain, identity, gasless API, session keys, and it works with existing frameworks like Anchor and all of the existing programs on Solana. Bolt can achieve order of magnitude more scale thanks to ephemeral rollups, which are game session that opens and close with users and scale on demand. And third, Bolt is lightning fast. We can achieve the same level of performance of traditional game engine before these dedicated runtime that can accelerate some operations, as we show you. This is a high-level overview of the Bolt framework. It's obviously built for Solana, but it works with any SVM-based layer, so potentially also on SVM-based L2s. And Bolt aims to do two things, to be composable and to bring scale. So the ECS, the Entity Component System, is one of the ways through which we simplify the reusage of on-chain components. And ephemeral rollups is the technology that I was briefly mentioning. We'll dig deeper into both of these aspects in a moment. And Bolt is integrated into the most commonly used game engine, which becomes the front end of the game. Obviously, Unity, but also other open source and loved game engine like Godot or Phaser. And we're even working with newer game clients like Turbo, which is focusing on improving the experience for the indie developers and facilitating the creation of quick games, and potentially more and more in the future.
And I will take it from here, and I will continue by explaining why we need an entity component system in ECS in the first place. And the answer is simple. It's because it's allowed to be maximally composable, which means that we can build, create, and reuse off-the-shelf components. So as the name suggests, ECS is built by three main elements. We have entities that are essentially just identifier registered to a word instance. And we have component which defines the data structure, so essentially the raw data associated with entities. And finally, we have systems, which is the logic that operates on components that are attached to the entities. So we have word instances, entities, components, and system that operates on those components. Now, this architecture has the advantage that all the system and components are reusable. They can be published in a public registry where developer can easily contribute, build, discover, and integrate it, any sort of components. So you don't have to write anymore from scratch your code, but you can reuse all the existing components and eventually contribute to it. We could, for example, have a data structure for a grid, or a movement system, or a zero-knowledge primitive for a fog of war. And I will now switch to my IDE, and I will show you an example of a simple word instance using the Bolt ECS. So we're going to define a couple of entities, a position component, and two systems which operates and change the data of this position component. So the first entry point is interacting with the word program. The word program is part of the Bolt framework, and expose a couple of extractions which allow you to register a new word instance. You can add the entities to your word instance, and you can register components to the entity that you just defined. And components are essentially, each component is defined by a component program where the component program has two instructions. So the first one, the initialize, create and allocate the space for storing the raw data that you will use in your component. So in this simple example, we are defining a position component. And if we look up the context of our initialize instruction here, we can see that we have our component data. And the component data is just defining a structure which has the x, y, z coordinates that can store, for example, a player position. Now, the second instruction, which is perhaps the most interesting, is an entry point that allows us to execute any logic. And is the one that will receive as input our component and an arbitrary system, and through cross-program invocation will execute the logic which is internally defined in the system. Now here, if you look at line 15, we have our CPI call, which through CPI will execute a logic internally defined. It perform all the computation the system is defining, and then returning our position, which the component program retrieve and set it back in our data. Now also let's try to look up the context of our apply function. And here we can see that we have essentially just two accounts. So the first one is the account containing our component data, and the second one is the system programs. So the system program is now an interface rather than a single program. So each programs which respect our bold system interface can be executed through this apply. And essentially this change the way you design your game logic and reverse the typical flow where if you want to create or encapsulate some logic in a program, you will typically add features, and each feature will be instruction in your program, and then eventually at some point your game program will be made immutable. With this paradigm, we can instead have a program which is immutable by day one, and then through this proxy mechanism we can inject systems which are built by us or can be built by anyone. So we have a game that runs forever, is extendable, and anyone can really change the logic or propose new systems which operate on those components. Now, the interface can allow also to do some checks. So we can perhaps have game mechanics where all the systems are permissionlessly allowed to modify the component data, or we could have interface that checks if the system is allowed to execute on the component. For example, you may foresee having a governance system where someone is proposing a new logic, and if the logic is approved, anyone will be able to use that logic in the game. And there could be also forks of the word. So in one word, you could have a flying system, while in the other, if it's not approved, you can have different set of rules, and everyone will be able still to contribute to this version of their words. So let's now investigate how we can build a system which modify this component. And a system is essentially just a program on Solana, where this program defines an execute instruction. And the execute instruction is the one we saw being called from the CPI, from the component program. And here it just encapsulates a very simple logic where it receives an input direction, a computed delta, and then change the x and y position of the component. So let's now see another system which could be potentially be built and deployed by someone else even after we release our games. Here is another example of a system which implements the execute, and here has increasing the z position by 1. So it's someone trying to add a flying system, which could be an interface having a different layer on your game. So now the idea is that all these systems, all these components are really composable, and all of the user of your game are not user anymore, but it's become an open, extendable, and persistent platform. So we'll now try to execute the unit tests that I have prepared in this example, and I will use the bold CLI, which is built on top of Anchor, so you don't have to learn anything new. If you're already familiar with Solana and how you build program on Solana, you can just build your program, test your program. So here I'm running bold build and bold tests, and here is executing our deploying our program and then executing the TypeScript test that I prepared here. So here, the tests are sending the transaction for initializing a new word. We are registering a couple of entities. We are attaching a position component to some of those entities. And then perhaps the interesting part is here where we execute some of this system. So here, we are calling the apply function. And then we are using one of the systems. So here is just a default system. Here we are calling simple movements, and then we have the fly movement here. And now if we look up at the logs of our test in the first transaction here, we're using the movement system with an upward direction. It's increasing the y position by 1. In the second transaction, we are moving on the right using the same system. And then finally, we execute the fly system, which is instead executing, increasing our z position by 1. So again, this is a simple example, but it gives the idea of a really powerful mechanism that allow anyone to build, extend, and potentially make your game be interesting forever. So we'll now go back to the slide, and I will describe the second interesting aspect of the framework, which is our scalability solution that use what we call ephemeral rollups. So the main intuition is that Solana is already super fast and cheap. It currently produces blocks with 400 milliseconds. You can process thousands of transactions. So it's really already suitable for building full on-chain games. But there may be cases where, for example, if you have all the logic on-chain of a multiplayer game, the positions updates could be too slow. So the main idea is that we can have an ephemeral acceleration layer, which is fully compatible with the Solana runtime, is optional, and it can serve as really an acceleration on specific operations, while most of the logic is still executed on the base layer. So it relies on the fact that on Solana, all the states are stored in accounts. Typically, you will have your game program defining the logic, and then all the states will be stored in this account. So we can delegate some of those accounts using the Bolt Air program to this ephemeral layer. In this example, there are two accounts storing the position of a player, which are delegated, and the provision is actively listening for delegations and provisioning requests. It will spin up on demand a new runtime, which is fast. It can be customized. It could have a gasless transaction or a ticking mechanism, and allow us to really have transaction below 50 milliseconds and potentially scale, having multiple dedicated runtimes. Now, the other interesting part is that all of this complexity can be abstracted from the user. So we have the RPC router, which is essentially exposing an interface as a traditional RPC router, RPC would, and client can just interact with the RPC, sending transactions. Since on Solana, all the transactions declare upfront all the writable and readable accounts which are used, this RPC router can essentially route both transaction and query of the data and retrieval to the correct layer. And then at some point, the ephemeral layer, as the name suggests, is ephemeral will close, and all the state will be settled on the Solana base layer, which is the responsibility of the sequencer, which keeps on track all the accounts. Another view of these mechanics is that we have two layers which execute transactions in parallel. We have delegated account which can be updated without throughputs and low latency, and then we have other accounts which are not delegated and are executed on the base layer. Now, the very interesting thing is that programs, tools, framework, infrastructure are on the base layer. You don't deploy your programs in the rollups, as is common in many other architecture. Everything is in the same layer. Everything is composable. And as we mentioned, also this specialized runtime can scale and can really be customized. Now, what this allows to unlock is really to have a full new category of games being built on the blockchain. So you can have low latency, high throughput games, as you would with a traditional multiplayer game server, but still being able to compose with everything that is available on the layer. One ecosystem, several tools, you can access liquidity, you can send messages through a protocol, mint NFT, use account abstraction, session keys, leaderboard. One unified ecosystem, everyone enriching a single state machine. Thanks for listening, and that was, you can sign up using the QR code to the early access of our framework, and please check out the repository. You can find already some documentation and the white paper describing in details the framework we just presented. Thank you very much.